I believe so, if everything looks right.
Sure does. We are ready on the power end, so you may begin.
All right.
Hi, I'm Rebecca Jang, a team lead of Cornell Rocketry, and I'm going to be presenting the overview slide. So this is our system overview. At the aft end of the rocket is the roll control system, which is our secondary payload. Towards the forward end of the rocket is our control landing mechanism and the target detection system, which are our primary payload. And in the nose cone is the tracer system, which is going to be doing tracking in flight electronics. I'm going to introduce Kevin Liu, presenting our airframe design.
Hi, my name is Kevin Liu. I'm the airframe sub-team lead at CRT. In this diagram, you can see the planned launch vehicle design for CRT. Our launch vehicle is a 5-inch diameter airframe, and it can be split into 4 separate sections. Starting from the aft end, the booster section is 47 inches long, the AV bay section is 30 inches long, and the CLM is 12 inches long, and the nose cone section is 39 inches long, for a total length of 128 inches. Below that, you can see all the inner diameter and outer diameter, all the tubing that will go into the launch vehicle. And take note that the motor tube that CRT is using is a 98 millimeter motor mount. In this diagram, you can see all the launch vehicle components. So again, starting from the aft end, the tail cone retainer will be a custom-made machined tail cone retainer, which will retain the motor as well as transfer thrust directly to the airframe, reducing the amount of shear in the centering rings. Next in the booster section is the RCS, or the roll control system. And then finally in the booster section is a section of airframe, which will hold the launch vehicle main parachute. The next section is the AV bay section, which consists of the AV bay and another section of airframe that is riveted in onto the AV bay. The AV bay will hold the altimeters and also cause 3 ejection events. The 3 ejection events will first be in the nose cone to eject the nose cone, which will be accomplished by running a wire along the outside of the launch vehicle. Secondly, there will be an ejection vent on the forward end of the AV bay, and lastly, an ejection vent on the aft end of the AV bay. The airframe riveted to the AV bay will contain the launch vehicle drogue parachute, as well as the CLM legs. And the CLM itself will be a tube of polycarbonate, which will be see-through so that pictures can be taken. The last section is the nose cone section, which consists of a section of airframe riveted to the nose cone. The section of airframe will contain the CLM parachutes, the nose cone parachutes, and a piston to provide a positive ejection system for those parachutes. And the nose cone itself will contain comms electronics, which will help track the launch vehicle. The materials selected for the launch vehicle were chosen for high strength as well as lightweight. So all fiberglass tubes will be G12 filament wound fiberglass, and all fins, centering rings, and bulkheads will be G10 fiberglass. The AV sled was selected to be 3D printed ABS plastic, which was selected in order to be customizable as well as to allow CRT to prototype. And the shock cord will be Kevlar, because Kevlar is stronger than nylon as well as more heat resistant. To continue, the motor retainer will be a multi-purpose 6061 aluminum, and polycarbonate was chosen for the CLM because it is clear to allow for pictures to be taken, as well as to have enough strength to act as airframe. And finally, all epoxy for fin fillets and binding fiberglass together will be using ES6209 air epoxy. The motor selected was a 98 millimeter Aerotech L1500T. The 98 millimeter diameter was selected in order to decrease the length of the motor and in turn decrease the length of the launch vehicle. And the specific motor that was chosen to have sufficient thrust to take the launch vehicle to the target apogee of 5,280 feet. The stability could be calculated using the center of gravity and the center of pressure, and as shown in the sample calculation, the projected stability of the launch vehicle is 2.87 calibers, having enough stability for a stable launch while not being overstable so that the launch vehicle cocks into the wind during high wind conditions. And the launch vehicle was simulated using open rocket, finding a projected mass of 50.7 pounds, target apogee of 5,283 feet, a thrust to weight ratio of 6.48, and a velocity off rod of 54.4 feet per second. In the table over here, you can see a sample simulation run in 0 mile per hour wind conditions. Our recovery system in the AV bay will consist of 2 RRC3 altimeters. As mentioned earlier, the AV bay will cause 3 ejection events. First, to eject the nose cone, second, to eject the CLM, and lastly, to eject and deploy the main parachute. So each RRC3 will cause 3 events, a main, a drogue, and auxiliary charge, and the 2 RRC3 altimeters will allow for redundant charges. In the first table, you can see the parachute sizing for each section of the launch vehicle. And in the second table, you can see calculations of drift in various wind conditions. Take note that in the worst case scenario of 20 mile per hour winds, every section of the launch vehicle drifts within the maximum of 2,500 feet required by NASA to remain in the launch field. In this table, you can see descent velocities as well as kinetic energy for each independent section. So if you look at the right column, you can see that every section of the launch vehicle lands with kinetic energy below the maximum of 75 foot-pounds. However, to ensure that all the sections of the launch vehicle remain in the field and do not drift, the descent velocity on the drogue parachute was calculated to be quite high, causing a high kinetic energy, a concern that CRT will explore in the future slides. In this table, you can see how each parachute is deployed and at what time during the flight each parachute is deployed. So starting from the top, the nose cone drogue will be deployed at apogee using a piston system. The nose cone main will be wrapped in a Jolly Logic chute release, which will release the parachute at 500 feet. The CLM drogue will be deployed at apogee plus 2 seconds when the CLM is deployed and ejected, and the CLM main will also be wrapped in a Jolly Logic chute release, released at 500 feet. The launch vehicle drogue will be deployed at the same time the CLM is ejected. Because the launch vehicle drogue and the CLM legs are in the same section, CRT is using the CLM ejection to pull the launch vehicle drogue outside of the airframe. To accomplish this, CLM is using a destructible rope system, connecting the launch vehicle drogue to the CLM. As the CLM deploys, the destructible rope pulls out the launch vehicle drogue, and then it shears so that the 2 sections can fall as 2 independent sections. And lastly, the launch vehicle main will be deployed at 500 feet using an ejection charge at the aft end of the AV bay. Some NASA requirements that were required for our launch vehicle included that the launch vehicle shall take a scientific payload to the target apogee of 5,280 feet. And this will be accomplished using our selected motor. And to account for variations of motor, the launch vehicle, CRT is able to add or take away ballast mass to target that apogee. Secondly, the launch vehicle must be recoverable and reusable. And to ensure this, CRT uses using strong materials to construct, as well as sturdy construction methods, so that after every launch, the launch vehicle can be recovered, reassembled, and then launched again. And all other NASA requirements can be found in our PDR documentation. Some team-derived requirements that are specific to CRT include that the wires connecting the nose cone to the altimeters must be able to separate. Because we are having an ejection event at the nose cone while still having only one AV bay, the wiring system along the outside of the launch vehicle must cause a charge in the nose cone, but also must separate in order to have 2 separate sections of the launch vehicle fall independently. So ground testing will verify that the separable wiring system will work reliably and consistently. Secondly, the parachutes without a launch vehicle section attached to the other end of the shock cord must be deployed. And CRT is using a piston system and the destructible rope system mentioned before in order to deploy those parachutes. And again, ground testing will ensure that those parachutes are deployed properly. The RCS bay must be accessible for construction and repair, and to ensure this, CRT is designing the RCS bay to be able to be slid in and out of the launch vehicle. And lastly, the communications bay must be available for construction and repair. And this is so CRT is able to put in the communications electronics into the nose cone. CRT will accomplish this by having a coupler be removable and rivetable so that CRT is able to open up the nose cone, put in comms electronics, close it up, rivet it, and then secure it for flight. And some failure modes that CRT is paying close attention to include the large kinetic energy on the drogue descent rate. Could lead to parachute tearing. So CRT is looking for ways to mitigate and decrease the amount of kinetic energy on descent from lowering mass to finding other ways to decrease the velocity. But ultimately, the subscale launch and the full-scale launch will judge the severity of this safety concern, and then CRT will look for other mitigation methods, such as using parachute bags, to increase the amount of time it takes for parachutes to deploy, decreasing the amount of shock on the parachutes. Secondly, a more complex recovery system increases the chance of some recovery failure. And in our subscale and full-scale launches, CRT will fully examine our recovery system in order to ensure that our recovery system is reliable and consistent. And lastly, if the destructible rope fails to pull out the launch vehicle drogue parachute or fails to shear from the CLM, there could be failures in recovery because the launch vehicle drogue parachute may not be deployed, or the two sections do not fall as two independent sections. And ground testing will ensure that the destructible rope can pull out the launch vehicle drogue, as well as to shear and have the two sections fall as two independent sections. Now I will introduce Connor Dempsey, our communications sub-team lead.
Hi, my name is Connor Dempsey. I am the sub-team leader of the communications team. So our NASA SL requirements are to utilize GPS data and radio transmission to determine the launch vehicle's position at all times during launch. We will be doing this by incorporating multiple GPS and radio transmitters on board the launch vehicle, which will give us the ability to know its position at all times during launch. We are also required to determine the location of the launch vehicle once it's landed. We're incorporating multiple redundancy systems so that in the case one of our GPS or radio transmitters fails, we have multiple other systems that can pick up the slack. For our CRT derived requirements, we are expecting to obtain video during flight. We're doing this through the utilization of a Raspberry Pi, which will be controlling the camera, and we expect to save and transmit all flight information, and we'll be doing this through utilizing a Raspberry Pi to save all the data, and then also a low-rod radio to transmit it down to our ground station. Next slide. All right, so these are some images that we took from last year's presentations. They show some of the technology we expect to use and some of the technology that we're moving away from. This is last year's TEM. We will be moving away from that. And then in the top left, you have the SRB and the GRB that are going to be modified to work more efficiently this year. Next slide. All right. So the simple radio beacon utilizes Morse transmission of its owner's call sign in order to allow us to use a Yagi radio to direction find. It requires minimal power and has the ability to transmit at 100 milliwatts, which should be more than enough power that we need to find the rocket once it's landed. Next slide, please. The GPS radio beacon transmits APRS packets that we're able to use with, we're able to collect with one of our handheld radios, which will enable us to determine our position relative to the landing position of the launch vehicle. And we have about an accuracy of a 10-meter range, so we should be able to find the launch vehicle with the utilization of this instrument. It is primarily being utilized as a redundancy system for the simple radio beacon in the case that it should fail, and it also transmits at 100 milliwatts. Next slide, please. So this year we're replacing the TEM system from last year with what's called the Tracer. So the Tracer incorporates a small computer, the Raspberry Pi Zero, an Arduino Uno, and a whole suite of sensors that will allow us to determine accelerometer, temperature data, gyroscopic data during flight. We will be transmitting the position data down through the LORA and receiving it on our GUI, which I'll describe more in the next slide. This is an overview of the systems that we plan on using. And shows a certain amount of the connections that we're using between certain parts of the system. Next slide. Right. So the ground station GUI. The LORA radio inside the launch vehicle will be transmitting data down to our LORA receiver, which will be connected to a directional Yagi, and we will be taking the data that we receive from the transmitting LORA and plotting it onto the maps and the 3D plot that you see here. This will enable us to better understand and better predict the landing position of the launch vehicle.